ሰላም ሰላም የዚህ ዩቲዩብ ቻናል ተከታታዮች፣ ይህ ማትማቲክስ ፎር ዩ ዩቲዩብ ቻናል ነው። ለዚህ ቻናል አዲስ የሆናችሁ ልጆች ቻናሉን ሰብስክራይብ በማድረግ እንዲሁም ይህንን ቪዲዮ ላይክ፣ ኮሜንት እና ሼር በማድረግ ለጓደኞቻችሁ እንዲደርስ ታደርጉ ዘንድ ጠይቃለሁ። ዛሬ በዚህ ቪዲዮ ይዤላችሁ የቀረብኩት የቤዚክ ማትማቲክስ ወይም ደግሞ ፍሬሽማን ማትማቲክስ ሰከንድ ወርክሺት ሶሉሽን ነው። ይህ ወርክሺት የተዘጋጀ በጎንደር ዩኒቨርሲቲ መምህራን ነው። ስለዚህ ከዚህ ወርክሺት የተመረጡ ጥያቄዎችን በጋራ እናያለን ማለት ነው። ስለዚህ አሁንም ወደ ጥያቄዎቹ ከመሄዳችን በፊት ደግሜ ማሳሰባችሁ ለዚህ ቻናል አዲስ የሆናችሁ ልጆች ቻናሉን ሰብስክራይብ እንድታደርጉ እና ለጓደኞቻችሁም ሼር እንድታደርጉ ለማሳሰብ ወደው። ይህን ካልኩ በኋላ ወደ ጥያቄዎቹ በምንገባበት ጊዜ ኦኬ የመጀመሪያው ጥያቄ question number 1, let x, y, z be three natural numbers such that x is less than y, y less than z. If the greater common factor of x, y and that of z is 3, the greater common factor of the next two natural numbers y and z is 15, and the LCM of these three natural numbers is given to be 3150. And the first natural number, that is x, is even natural number which is greater than 10. Then we are asking just to find the corresponding value of x, y and that of z satisfying this condition. Therefore from here the three natural number x, y, z, their greater common factor is 3. That means the only common factor of these three natural numbers is this one, that's simply 3. So that the only common factor of this one x, y and that of z is only 3. Next information given, which is given here, will be the least common multiple of the three natural numbers is 3150, which can be factorized in this way. That means from this prime factorization of their least common multiple, all the three natural numbers will have a common factor which is the combination of these four, that is 2, 3, 5 and that of 7, so that there is no any other factor other than this 4 which is a factor of either of these three. And therefore the next one is the greater common factor of y and z, that is next natural numbers that is given here. It is already 15, and which can be factorized as 3 times 5. So that when we go to that of the individual values of the natural numbers x, y and that of z, we know that the common factor of the first natural number or the smallest natural number, that is x, could be 2 and that of 3. 2 is the factor of this one because just we are informed here x is an even natural number greater than 10, and 3 is also the possible factor of this one, that is x, because the greater common factor of the three natural numbers is given to be this one, that is simply 3, so that 3 must also be the second common factor of the first natural number, which is x. Then the next one, that is y, the possible factors of y will be 3 and that of 5. 3 is the first common factor because 3 is the greater common factor of the three natural number from here, and also 5 is the other possible factor of y because the greater common factor of y and that of z is 15, so that the factors of 15 are 3 and that of 5. And next, that is z, the common factor of z could be 3 and that of 5 because of the greater common factor of y and z, and it's also a 7 because here there exists a certain condition that must be satisfied. That means x must be less than y and y must be less than this one, that is third natural number, which is 8. So that this one x is 2 times 3 square. We can take this one, that's simply 3 square, to be that of this one, just to make x to be the smallest of y and that of z. And as this 5 square could be taken from this one, which is the other factor of second natural number y, and for that it is 3 times 5 times 7. So that the corresponding values of these three natural numbers would be 18, which is 3 times 3 square, y is 75, which is 3 times 5 square, and the product of these two, that is it could be 105. So that if we observe this condition here, it is satisfied, that is x18 is less than 75, again 75 is less than that of 105. Okay, the second question will be question number 4. It says 4 satellites revolve around the Earth once every 6, 8, 10 and 15 hours respectively. If the satellites are initially lined up, how many hours must pass before they will again be lined up? That means what we are given here is we are given 4 satellites which are revolving around the Earth, so that for the complete revolve around the Earth, the first satellite needs 6 hours, second needs 8, third is 10, and the fourth satellite needs 15 hours. Therefore, after revolving, after a certain time is passed, these 4 satellites again will found on the same line, or simply they becomes lined up. So what we are asking here is, we are asking just to find the time necessary for these satellites to be lined up for the second time. Therefore, and actually the given information is here, that is 6, 8, 10 and 15 are 4 satellites orbiting there, and initially they are lined up, they are found at the same, or simply approximately on the same line, and the main required thing here will be the number of hours passed before they will lined up. So here the necessary time necessary for the satellites to line up again will be the least common multiple of their corresponding hours, that is corresponding hours 6, 8, 10 and that of 15 hours. So that the LCM of these hours will be this one, that is 2 to the power of 3 times 3 times 5 by using that of prime factorization, which is equal to 100 hours. 120 hours. You know that 120 hours means it is just about this one, that is 5 days. Therefore, these 4 satellites which can revolve around the sun within this time interval becomes lined up for a second time, or simply just to become lined up they need 5 days or 120 hours. The next question is question number 6. So it's express the following numbers in decimal form. That means converting the fractional form of a given rational number to that of decimal, or decimal to that of fraction. But what we need here is, what we are asking here is, we are given a fractional form of a given rational number, and we are asked just to express, or simply to find the corresponding decimal form of a given rational number. The only thing that we can use here just to obtain the decimal form of the given rational number could be only applying long division method. So that using this technique, for example, the first one, that is a 1, if we divide 1 by using that of this one, that is 8, so that we can obtain this terminating decimal, which is 0.15. That means we have to divide this 1 by 8 until we obtain a remainder that is 0, or a digit which repeats itself in a certain pattern, so that his terminating decimal, which is 0.15. Similarly for b, if we divide this one by using 7, so we have this one 0.2857, 1 for which is repeating decimal. And lastly, c, that is 23 over 11 is 2.09, where 0 and that of 9 are repeating digits. Next question is question number 8. It's a theorem. It says, show that a natural number n is even if and only if n square is even number. So what we are given here is so they're just given any natural number. If the given natural number is even, so that its square is even, or if the square of a certain even natural number is even, then the natural number itself is even. You know that this theorem is biconditional. That means it is if and only if, so that if we write this one in separate way or simply add the combination of two implications, we have this one, that is if n square is even, then n is even. This could be the first one, the first implication. And next one, if n is even, then n square is even. So in order to prove, for example, if we consider the forward or simply the first component of this biconditional statement, we have to apply proof by using that of contradiction. We know that if n square, that is the first component of this one, is if n square is even, then n is even, so that the contrapositive of this could be if n square, if n is not even, that is if n is odd, then n square is odd. So that in a statement form, it could be this one, that is if n is odd, then n square is odd. So let us start our proof by starting or simply assuming that, or simply taking an arbitrary natural number, that is n, which is odd. So that if this n is odd, so that the natural number, that is n, could be written in this form, that is twice of x plus 1, where k is any natural number. Twice of k is an even number, plus 1 could be really an odd natural number. So if the odd natural number is written in this pattern, what will be the square of this natural number? Could it be an even natural number or odd natural number? Let us see it. You know that if n is this one, n square could be the square of 2k plus 1 square. So the square of 2k plus 1 square will be 4k square plus 4k plus 1. Then what will happen if we factor out to add a common factor for the first terms of this trinomial? We have this one, that is 2 into twice of k square plus 2k plus 1. We know that the term which is enclosed by using that of this bracket is k is any natural number. The square of any natural number is natural. Twice of natural number is again natural. So that the sum, or simply this expression, is natural. So twice of a certain natural number plus 1 will be, it is an expression for, which is suitable for an odd natural number. So that this is odd natural number. So since we proved it is contrapositive to be true, the contrapositive of this one, that means, which is if n is an odd natural number, then n square is odd, so that this is true, which is equivalent to that of this one, since this one is the contrapositive of the first one. Therefore, then the original statement, that means the original statement in this case, if n square is even, then n is even, is also true, so that this would be the proof of this theorem. And it is similarly we can prove the converse, that is if n is even, then n square is an even natural number. But the converse of this statement will be left as an exercise for you. The next one is question number 9. It says express the following numbers in the form of this one, that is over b, where a and b are natural numbers, and one thing that should be included here will be b must also be different from that of this one, which is 0. So that if we start from the first one, that is a, we know that in order to find the fractional form of a given decimal number, the only thing that we can do will be just multiplying by using that of a certain fraction of this form. We know that we are given this one, that's 1.0015, so that here this decimal has 5 number of digits, or simply decimal. The digit is just after the decimal point. Therefore, in order to take this decimal point to the last digit, that's simply here, we have to multiply this one, or the decimal point, or the decimal number itself, by 10 to the power of 5 over 10 to the power of 5. Or we know that this is already 1. and 5 stands for the number of digits just after the decimal point or to the right of the decimal point. Then when we multiply this by 10 to the power 5, we will obtain this one, that is 100,125 over 10 to the power 5. Or so that here the is formally the fractional form of this number, but in order to make it formal or simply usual, we have to make the greater common factor of the numerator and the denominator to be that of 1, or the numerator and the denominator must be relatively prime numbers. So that by further simplifying the numerator and the denominator of this one, we can write in formal way, or simply having a greater common factor, which is 1, that is relatively prime. Or we can put like as it is, but it's better if we simplify further. The next one, that is B, is 2.013214, where 1 and 4 are repeating digits, that is repeating decimal number. Then in order to find the fractional form of such a decimal number which is repeating, we have to find, or simply we have to multiply the decimal number itself by using that of an expression, that is 10 to the power of 6, where 6 is the number of the sum of digits after the decimal point, that is a sum of repeating and non-repeating digits. Here we have 4 non-repeating digits and 2 repeating digits, which are totally 6, minus 10 to the power of 4. 10 to the power of 4 means the number of non-repeating digits over the same expression. So when we distribute this one over the numerator, the difference between 10 to the power of 6 minus 10 to the power of 4, and further take the difference, we can obtain this one, that is 1,993,82 over 990,000. So like the thing, or simply I have told you here, we have to make, or simply we have to further simplify this fraction into its lowest term, or having a greater common factor of the numerator and denominator to be 1. So this could be your work. The next question is question number 10. It says determine the truth value of the following by justifying. Just truth value which needs a certain justification. First one, that is A. It says the sum of two irrational numbers. The sum of two irrational numbers is a rational number. We have a rational number here, so that if you take any two rational numbers, the sum is also rational, because just so we know that set of rational number has a closure property with respect to all the four usual mathematical operations except dividing by the specific value, that's simply 0, so that the sum of any two rational numbers could be rational, so that the first one is true. The second one, that is B, we have the sum of every two irrational numbers. It is an irrational, which is not rational, is an irrational number. So if we assume that the sum of every, it is every, so if you take for example the irrational numbers which are opposite to each other, the sum of any two opposite numbers is 0, so that the sum of two irrational numbers can have a possibility to be that of 0, which is not irrational or rational, so that the truth value for this statement could be false because of the existence of that of the sum of two irrational numbers to be rational. The third one, that is C, the product of every two irrational numbers is an irrational number. The product of two irrational numbers is an irrational number. If you take just to falsify this one, that we know that for example that is radical 2 in the usual or simply known irrational number. If we multiply radical 2 by itself, that is radical 2, the product is 2, which is not irrational or rational number, so that the existence of such a condition, the truth value for C will becomes false. The last one, that is D, if X is an irrational number and Y is rational, then the sum of irrational plus rational number is rational. No, because this is an irrational number and this one is rational, so that the sum of an irrational number and rational number cannot be rational, rather it must be an irrational number, so that the statement, or simply the truth value of this statement, will be again false, so that it's false. Next one, that is question number 3. Question number 11 is about the proving the irrational number, that is radical 3. Show that radical 3 is an irrational number. We know irrational 3 is irrational. Radical 3 is irrational, but how can we justify it as irrationalness is the problem. So let's apply proof by contradiction. By contradicting, so that when we contradict this one, we are given that is radical 3 is an irrational number. So let's assume that radical 3 is not an irrational. If it is not an irrational, let's assume that radical 3 is a rational number. So if it is a rational number, it must be written in the form of a or b, satisfying this condition. That is, radical 3 is equivalent with a over b, where b is different from that of 0 and n b are integers with this condition. Don't forget this one, that is n b are relatively prime numbers. So if the rational number, that is radical 3, is written in the form of this one, what will happen if we take the square of both sides? If we take the square of both sides, the square of radical 3 is 3 and the square of this fraction is a square over b square. If we multiply cross multiplication like this, that is, or if we multiply both sides of this equation by b square, we can obtain this one, that is 3b square is equal to a square. So that from this expression we can have, or simply we can easily clearly see that a square is the multiple of this one, that's simply 3, or 3 is a factor of a square. If a square is a multiple of this one, a itself is a multiple of 3, or 3 divides a square, so that if 3 divides a square, or a square is a multiple of 3, a itself is a multiple of 3, so that 3 divides this one, that is a. So let us call this one to be star. Next, if a is a multiple of this one, that's simply 3, or 3 divides a, let us express this one, that it means that there exists another natural number or integer such that 3 times that integer gives this one, that is a. This could be c, and a is equal to 3c, since 3 is a factor of a, or a is a multiple of 3. Then if we square both sides of this one, that is a is equal to 3c, we can obtain this one, that is a square is equal to 9 square. But what is a square? From here, a square is exactly equivalent with this one, that is 3b square, so that 3b square, or 3b square is equal to 9c square. If we divide both sides by this one, that is simply 3, we can obtain b square is equal to 3c square. Hence, from this again, that 3 is the factor of b square, or b square is a multiple of 3. If b square is a multiple of 3, b itself must be a multiple of 3, or 3 is the factor of b, that is 3 divides b. So that if 3 divides b square, 3 must divide b, so let us call this one to be double star. Then from these two things, from star and double star, above and we have at least 3, which is the common factor, and this contradicts our assumption that the greater common factor of a and b is 1. So that in this case, because of this contradiction, our supposition or simple assumption is false, that is a greater common factor of this one, that is 1. Therefore radical 3 is an irrational number. The next question is question number 12, which is use principle of mathematical induction just to show that these theorems are true. So if we start from the first one, that is a, which is 1 square plus 3 square plus 5 square, 1 plus 3 plus 5 plus twice of n minus 1, or the sum of the first n number of odd natural numbers is equal to n square. So in order to apply this technique, that is mathematical induction, for proving such a theorem, as you know, we have to check first that whether the theorem is true for the first few natural numbers. For example, if n is 1, twice of n minus 1, that is simply 1. We have only 1, and his 1 square, which is true, so that it holds true for n is equal to 1. For n is equal to 2, we have 1 plus twice of 2, that is 4 minus 1, that is 3, these two factors, so that in this case we have 4, that is 2 square, which is equal to 4. So that the next thing will be, let's assume that the theorem, or simply this expression, holds true for n is equal to k, which is where k is an arbitrary natural number. So that in this case, this theorem, or simple expression, could be written in the form of this one. Then our claim will be, what will happen if the theorem it clearly true for the next natural number for n is equal to k plus 1 or not. So we have to check this one. Then from the original statement here, or the thing which we are taking here, so we have this one. So what will happen if we add the next natural number to both sides of this one? We can obtain this one, that is the sum of twice of k plus 1 minus 1. We have twice of k plus 1 minus 1. So that the simplified form of this expression could be this one, that is k square plus 2k plus 2 minus 1, which is k square plus twice of k plus 1. And we know that this trinomial is the square of a certain binomial, which is the square of k plus 1. Therefore, when it was k square. When it becomes k plus 1, it becomes k plus 1 square, which is that this expression is equivalent with this one, that is 1 plus 3 plus 5 plus twice of k plus 1 minus 1. Therefore, the theorem holds true for every k, or the theorem holds for any natural number. The next one, that be 1 square plus 2 plus this is just to say 2 square plus a square plus n square is equal to n into n plus 1 times twice of n plus 1 over 6. So that again, using principle of mathematical induction, we have this one. So let's assume that this theorem holds true for an arbitrary natural number k, which is an element of n. So our claim will be checking the trueness of this theorem for the next natural number, which is k plus 1. So if we assume that this is true for n is equal to k, we can obtain this one, that is this equation is obtained directly from this one by only replacing k in the place of n here. So our claim will be, is it also true for n is equal to k plus 1? So let us check. What we can expect here is, if for k, if the expression is this one, for k plus 1 it must be, or we must assume that this could be k plus 1. If this one is k plus 1, k plus 1 plus 1 will be k plus 2. This could be twice of k plus 1, that is twice of k plus 2 plus 1, that is twice of k plus 3 over 6. What we expect, the expected expression in this one. So just let's add the square of the next one, that is k plus 1 square, to both sides of this equation, and we'll obtain this one. So this equation is directly obtained from this one by only adding the square of the next term, that's k plus 1 square, k plus 1 square. Then if we add this one together, we can obtain, that is k into k plus 1 times twice of k plus 1 plus 6 into k plus 1 square. We have a common factor that is k plus 1 here. If we factor out this k plus 1 at the common factor, we'll obtain this one, that is k plus 1 into what's left here is only k times twice of k plus 1, and here 6 times k plus 1 will be left. Then when we distribute this 1 over here and multiply this term by 6, we can obtain this one, that is k plus 1 plus twice of k square plus 7k plus 6. But the term which is enclosed by using that of this square bracket is factorizable, so that we can factorize this one as like this: k plus 1. The factorized form of this one is k plus 2 times twice of k plus 3, which is directly equivalent with this expression. So that what we expect here was this k has to be k plus 1, so that it's k plus 1. K plus 2 will be k plus 1 plus 1, that is k plus 2, and twice of k plus 1. If we substitute k plus 1 here, we can obtain this one, that is twice of k plus 3, so that the theorem holds true for every k or for every natural number. The last, based on the mathematical induction, is 3, that is 1 over 2 plus 1 over 6 plus 1 over n into n plus 1 is equal to 1 minus 1 over n. And therefore, using again the same principle, that the principle of mathematical induction, we have this one. But if we subtract this one from there, this could be written in another form. So let's assume anyways the theorem holds true for n is equal to k. So that when for n is equal to k, if we substitute k in the place of n here, we can obtain this expression, and the difference between these two could be k over k plus 1. So our claim will be checking the truthiness of this theorem for the next natural number, that is k plus 1. When in k plus 1, we can obtain this one. This is obtained from this statement by only adding this term 1 over k plus 1 into k plus 2, 1 over k plus 1 times k plus 2 to both sides of this equation. Because 1 over n into n plus 1, we are assuming that n is equal to k plus 1, so that the last term will be 1 over, if we substitute k plus 1 here, we have k plus 1. For k plus 1 for the next n, that is k plus 1 plus 1, which is k plus 2. The same holds true for the case of this one. Then the sum of these two, that is we have k over this 1 over k plus 1. So we can factor out 1 over k plus 1 at the common factor. If we factor out this one, we can obtain this one, that is 1 over k plus 1 is taken, so that only k will be left here. 1 over k plus 1 is taken, so that 1 over k plus 2 will be left. Then the sum of the terms which are enclosed by the square bracket could be this one, that is k square plus 2k plus 1. But k square plus 2k plus 1 is a perfect trinomial, which can be expressed as the square of a certain binomial, which looks like that of this one. So k plus 1 square, we have 1 over k plus 1, so that this k plus 1 can cancel one of the two factors, that is k plus 1 here. So what's left here is k plus 1 over k plus 2. If we take long division method for this one, we can obtain 1 minus 1 over k plus 2, which is the expected one. Therefore, the theorem holds true for every k or for every natural number.